Pipeline Industries Guild webinar. We've got Ken Lax on again. Fifth presentation he's done for us on pipelines and cathodic and electrical protection of pipes. He's like our Taylor Sheridan in terms of the number of fans. Again, 19,000 on one of the presentations he's done. If you do want to check out any of Ken's previous presentations, if you go on YouTube and look for Pipeline Industries Guild, we've got over 100 webinars there now, and you'll have Ken's 4 previous ones. Today's is Pipeline Designer's Guide to Cathodic Protection. If you've got any questions, please put them in the chat and we'll answer them at the end. But over to you, Ken.
Yes, thanks, Sean. Good afternoon, everybody. Just to put Sean right, today's presentation isn't about the design. It's can't get back to my shared screen. So there we go. It's about the electrical impact assessments for pipelines due to interference from alternative energy sources. And as you're all probably aware, it's a hot topic at the moment because there's so many of these things going on, and it's outside the knowledge area of most pipeline operators, and the guild has takes the initiative to do these presentations to share knowledge throughout the guild so that you can learn things about something which is outside your own area of expertise, which is always a good thing. And particularly in the case of electrical interference to pipelines is, of course, the personal risk that comes with it. If you're a pipeline operator and you ignore some of these things, you could end up in trouble. As Sean said, there have been several in this series that the Guild has initiated, which you can find on YouTube. If you have any trouble, you can contact the Guild and they'll give you the links to follow them. The presentation has been prepared by myself and Professor Haralambos, who is obviously a PhD electrical engineer with a long experience and interest in AC and DC interference to pipelines. Myself, I've been a member of PIG, I think for 30 years, maybe a wee bit less, and I've represented the Guild on the international and national technical committees in respect of cathodic protection, electrical interference and coatings. So between us, we have got quite a bit of expertise. I'm going to start off with an interesting fact, which every time I present it never fails to shock me, that the estimated global annual cost of corrosion is $2.5 trillion US, which is enormous. And they estimated that about 80% of that cost could be lost if only people followed existing technology and techniques. So it's a bit of a condemnation on some industries that they don't take better care of their pipes. Obviously, the people who look after high pressure gas pipelines and oil pipelines are a bit more aware of this than perhaps the utilities are, working on the old premise that if you get a leak from a water pipe, it's not the end of the world. I'm afraid that premise is no longer true, especially now that we have pipelines in energy corridors and there are occurrences of leaking water pipes that have washed away the support for high pressure pipes. So what we're going to talk about today is I'm going to have to give you a bit of a refresher on external corrosion on pipelines and what we do to protect them, to stop them corroding. And then we're going to explain how stray currents affect that process. And then we're going to look at impact assessments and mitigations. As usual with my presentation, I don't assume any electrical or electrochemical knowledge. And for those of you who do have electrical or electrochemical or even degree level physics, you can just close your ears at certain points in the presentation because you'll find it embarrassingly simple. Well, we've got this mad dash to net zero, and alternative energy systems are sprouting up everywhere. I can't tell you how many inquiries pop across our desk every week for these things, because a lot of it is speculation. Somebody will see a nice empty field and they take an option on it, and then they try to get planning permission for a solar farm or a battery energy storage system or something like that. And they're putting a planning application. The pipeline operators are 99 times out of 100 informed about this planning application, and they immediately want to know what the electrical impact is going to be on the pipeline. And during this presentation, I'll be explaining to you why these apparently unconnected things are all connected and can cause a problem for us. And it's not always the obvious things. We look at the kind of energy systems you probably all know about, like the solar farms, the photovoltaic systems, wind turbines. Some of you may know about battery energy storage systems. Probably not everybody will be aware of energy balancing system, synchronous condensers, and high inertia condenser systems, HICS. And we'll be explaining these as we go along. But they all do provide an increased risk to the pipeline, which at the time of design and construction is often not quantified. And there's also the hidden risk that if you have a pipeline minding its own business buried in a rural area, the pipeline risk from lightning strikes would have been evaluated and considered to be pretty low. Unfortunately, some of these systems, especially wind turbines, do increase the risk of lightning strike on the buried pipeline. And as we'll explain to you a bit later on, a lightning strike is a massive wallop of current into the soil, and it disperses through the soil and does affect the pipeline even at quite significant distances. So we do really need to keep those in mind as well. So I'm going to give you a little reminder about corrosion. Those of you who've watched my presentations before will be familiar with this. But essentially, you never get something for nothing in this life. And if you dig up a piece of ore and you add lots of energy to it by digging it up, transporting it to the surface, taking it to a foundry, throwing it into some furnace with some other bits and bobs, and then spewing out at the end some steel, you've added a lot of energy to that original ore, and that's not where that ore wants to be. So because of the laws of conservation of energy, as soon as you leave that piece of steel, it will start to revert to being a crumbling ore. The only question is how long it's going to take. If it's sitting in a very corrosive atmosphere, for example, or an environment like acidic soil or resting in acid or contaminated soil, the process will be quicker than if it's just sitting in dry sand. Now, corrosion is an electrochemical process. That means there's an electrical part to it and there's a chemical part to it. And you can stop corrosion by changing either one of those two parameters. Practically speaking, for buried pipelines, which is what we're going to be talking about today exclusively, it comes down to electrical resources to provide the cathodic protection, and for pipeline coatings or tapes to provide the electrical resistance. And I'll be explaining to you a little bit about electricity as we go on. But what you should bear in mind is that if you have 1 amp DC leaving a carbon steel pipe or any bit of carbon steel in the soil, it will consume approximately 9.1 kilos of steel. It varies a little bit depending on the type of steel and the type of soil, but as a general principle, 1 amp DC, 1 year, 9.1 kilos of steel. And when I first started in the corrosion industry, the coatings weren't anything like as clever as they are now. Even the tapes, you might think to yourself, oh, a bit of waxy tape wrapped around a pipe's not very high tech. But in fact, the modern tapes are extremely good. The adhesion is good. The longevity of the product is good. And we are gradually weeding out cowboys who apply it badly. It's probably fair to say that most tapes systems fail due to poor application, not due to the product itself. So we put the tape on because it's high resistance and it reduces the current flow. And we then apply cathodic protection to provide the parts where the coating is damaged during installation or during excavation. Now here's the bad news. The coatings have improved so much that when they fail or get damaged, only a small part of the pipe steel is exposed. In the old days, it used to fall off in sheets. Now it doesn't, which means that 9.1 kilos of steel is only in the area where the coating is defective. And we use a kind of nominal coating defect size of 1 centimeter square. So if you've only got 7 to 10 millimeters of pipe wall thickness, and you're going to lose 9.1 kilos of steel per amp per year, and you're near to a solar farm that's dumping its current onto the pipe, and the pipe leaves at the coating defect, you very quickly exceed that 1 amp DC, and the corrosion will be very quick and be like a hot knife going through butter. So we do worry about small amounts of current and small voltage changes, which we'll come to in a moment. We use the tape because it has a high resistance, and there's a general law in electrical systems called Ohm's law, which basically says that if you're trying to push something through a conductor like a pipe, then the thing that pushes that energy through the pipe is the voltage. So the voltage is the driver, and the current is what you get out of the other side. And if you have a high resistance, then you get less current out. If you have a low resistance, you get more current out. So it's really pretty straightforward. It isn't rocket science. And cathodic protection is the way that we generally protect the pipe in combination with coatings. You don't need coatings. You can protect bare steel pipes. Offshore platforms, for example, are very often bare steel. But you need a lot more cathodic protection current. And for that reason, for reasons of economics and longevity, we apply cathodic protection. And cathodic protection is just a simple system for squirting current onto the pipeline. And it's no more complicated than that, as I'll explain a little bit further on. So you've got to have some current flowing onto the pipe to protect it. Now, it's all about energy, as I mentioned earlier on, and the movement of charge and energy is everything that controls pipeline corrosion. So it's hard to measure that energy. But one of the ways we can get an idea about it is by measuring a voltage. And we measure the potential of the pipe with respect to the soil. We have a special widget that we put in the soil to give us a consistent contact, so you can compare the voltage from day to day, year to year. And we know that in its natural state, a pipeline will have a voltage of about 0.5 volt, roughly speaking. And a well-protected pipeline will have a potential of about 1.2. We won't worry about polarities for the minute. So you've only got 0.7 of a volt difference between a very well protected pipe and one that's corroding freely. So that's a bit of an oversimplification because there's a time element involved as well. But you can see from that why we do worry about changes in voltage, especially long-term changes. Now, this is my famous basic electrical drawing, and if you start off with the premise that electricity is weird and hard to understand, that's a good starting point. It comes in two flavors, really. It comes in direct current, which is what you get from a battery, and it comes in alternating current, which is what comes out of the socket on the wall of your house. The DC is very easy to understand. There's no great intellectual power required. If you have a power source like we have on the left, and you have a load like we have on the right, the power source could be, for example, a battery, and the load could be a lamp. And I think we all understand that until the switch is closed, you won't get any light. When you close the switch, the light comes on. Nothing magic there. Now, you can now think of the power source as the cathodic protection system, whether it's galvanic anodes or what we call impressed current, and the load would be the pipeline. So you won't get any protection going onto the pipeline until that switch is closed. And very often that the cause of that of CP failing is a broken cable, which is equivalent to the actual switch being broken. Now, there is quite a lot of maths around and science around to sort out AC, because it is a bit more complicated. It doesn't quite see things the same way that DC sees things, so we have to do special things. But this is a formula which anyone who's done physics will perhaps recognize. It's some calculus that allows you to calculate the position of the charges in an electric field. And I have to say, it's not intuitive for people to look at that and see what it's telling us. So I've come up with a scheme to explain it, and I'll probably be thrown out of the Institute of Corrosion for explaining it so clearly that they might lose some business. Now, this shows you absolutely everything you need to know about electricity and pipelines and corrosion. If you imagine the little ball sitting on the plank on the seesaw, if the plank is level, if it's flat, that little ball, that charge, won't move. The only time electric current will flow in a CP system or in the soil is if there's a slope, like shown on the right. And it's a simple analogy. Imagine a plank of wood and a marble. It's the same phenomenon. You get a big gradient, big things happen. So you can substitute on this little plank. Instead of having weights on each end to keep it balanced, think of the voltages. So if you have a big voltage on one side and a big voltage on the other side of the same magnitude, there won't be any flow of current. And if it's the other way around, you've got a big voltage on one side and nothing on the other side, you get a big flow of current. Now, it doesn't get any easier than that. It really doesn't. And I'm just going to show you how that applies throughout cathodic protection. It's a nice diagram that Professor Haralamva's put together to illustrate the principles, which you can look at your leisure afterwards. But what it means is that the little rings that you're looking at here, these are equipotential rings showing how they're very close together near the source and they get further apart as you go away. It's not an inverse square law when it's going through the ground, but it does decrease in a rather orderly manner. You can see the shape of the curve here, and you can see where the charges lay on the different levels, so that in this case, because they've got a different potential or a different weight here and a different weight there will be a flow of current. And for those of you who work on pipelines near overhead power lines, I hope you've been taught that if you see a conductor broken on an overhead power line and it's touching the ground, the thing that you mustn't do is run away, because then the length of your stride will be enough to have a big voltage difference between your 2 feet. And if you have your 2 feet at a big potential difference, the current will flow through your body, and you don't need much to kill you. Thousandths of an amp will kill you if it goes across your heart. If you do happen to be in the situation where a conductor like that falls on the ground, your safest bet is put your 2 feet close together and do little bunny hops and hop away from the source of the current. And because you're doing these bunny hops and your feet are close together, they'll always be at the same potential. So that's an important and rather simple example of how it works. Same thing happens if you're looking at electric shock risks, which is something that we also have to consider in our assessments. Electric shock risks generally come under fault conditions, but if there's enough induced voltage, it can also be under static conditions. And if you touch things that are at different voltages, you'll get a wallop. And that's why you have to be really careful when you're working in these sort of areas. So I'm going to explain a little bit to you now about AC, because when you distill it all down, there are 2 main kinds of electrical interference to pipelines that cause us problems, both for safety, personnel safety, and for corrosion. And one is alternating current. And an alternating current, as I mentioned, is what comes out of the socket on the wall, and it varies 50 times a second in the UK. So the frequency that it changes is 50 times a second. So you get one of these cycles here in 50 seconds. That's from there to there. And with every electric current, there is always a magnetic and an electric field. It can't be avoided, whether you're talking about the level of electric current that exists in an atom or an electron. You still have a magnetic field and an electric field associated with it, although it's very weak. And indeed, it's the changing magnetic fields, or the magnetic fields in the electric charges, that propel it. By the as you know, if you put 2 similar poles together, they repel, and that adds partly to the movement of electrons in all objects, really. So when you're looking at AC, you've actually got 3 things that are varying at the same time. You've got the up and down of one wavelength, you've got the side to side of the other, and it's all going forward as well. It's all moving in this direction, which makes it a vector, really. So what it means is that with batteries, you can add them together. You put 2 12-volt batteries in series, you get 24 volts. You put 3, you get 36 volts. It's different with AC. You have to calculate where you are on the waveform at any particular time with respect to anything else. But the important thing to remember about these varying waves is that they're invisible. You can't see them, and there is an inviolable law that says if you have a conductor in a changing magnetic field, it will induce a voltage in the conductor. So although you can't see it, you could be near a structure that's getting electricity induced in it because of these fluctuations. And the magnitude of the voltage that's induced is proportional to the current and to the rate of change. So a rapidly changing field will induce more of a voltage than a slowly changing field. And the higher the current, the greater the induction. Overhead power lines tend to run at fairly set values, starting at 10,000 volts, running up to 400,000 volts. And you can imagine if you've got 400,000 volts, there'll be quite a lot of current flying around. It could be in the thousands of amps. And under fault conditions, you get induction and another effect, which I'll tell you about in a moment, which is called conduction. So AC is a risk for pipelines, and we have standards that tell us how much we can tolerate. As a rule of thumb, you start to pay attention when you induce more than 15 volts into a pipeline. And of course, a pipeline is a very long, thin conductor. So with induced voltages, what we worry about mostly is the co-location or the parallelism length between the overhead power lines or the buried power lines and the pipe. People tend to get the idea that crossings are the risk, but in actual fact, crossings are not the biggest risk at all. The biggest risk is the length of the parallelism. So just because you can't see it doesn't mean it's not there. So we discussed that you'll always get this voltage induced. Indeed, it's how generators work. That's why they whiz round and round and round and round, so that they can have either a rotating magnetic field or a rotating conductor. Either way, it doesn't care. And the other important thing to notice is that the voltage is induced on the pipeline regardless of its coating. It's exactly like a radio wave. It's no different from the radio waves that come from radio transmitters, broadcast transmitters. And if ever you played with radios and aerials when you were younger, you would have realized that a coated aerial still receives signals in exactly the same way as a bare wire does. So there's no protection at all from AC induced voltages provided by coatings. Now, conductive interference is a little bit different. And conductive interference is interference that is carried through the soil or through another conductor. In our case, we're talking about interference through the soil. So the soil has a resistance. It's rather difficult to analyze how the current travels through the soil because it travels in many different layers and it travels at close to the speed of light and difficult to know where the current's been by the time it arrives somewhere. So when we model the effects of conductive currents on the pipeline, we are forced to do some soil analysis, some fancy soil analysis to try and see how the current's going and what the effective resistance is. You can do this, excuse me, you can do this in CP by analyzing the soil resistivity data using what's called a Barnes layer analysis, which works out the resistance or the resistivity of the soil at different depths. It does it much more cleverly in modeling software. And that's generally what has to be used when you get into complex situations. Now, the conductive interference risks are always there with DC leakage because, as we'll see a little bit later on, any DC current that doesn't go back to the source via the intended route will leak through the soil. And if it sees a coating defect on the pipe, it will follow that path back. And if you happen to be unlucky enough to have another defect close to the source, it will leave the pipe at that point and get back to its source. An electric circuit has to be complete. So it will always get back to its source. Otherwise, you won't get any current flowing. It's like having the switch open. The AC systems, on the other hand, the predominant mechanism is inductive, but when there's a fault between one of the phases and the earth, you get the current flowing in the earth, and these currents are usually quite high. It's not unusual to look at substation fault currents of 35,000 amps. The good news is it doesn't last very long. It automatically shuts down and does all kinds of clever stuff. And it varies how long it takes to shut down. Modern systems, about 0.2 of a second. Older systems could be up to 1.5 seconds. Now, from the pipeline point of view, this conductive interference doesn't directly and immediately affect the corrosion risk. And it's wrong to think that these very high voltages will blow the coatings off. That seldom happens, and not under these kind of fault conditions. What it can do is it can change the characteristics of the coating. The coating has a dielectric strength, which means basically it tells you how good an insulator it is. And you've probably seen insulators on overhead power lines. They're quite long and they're ribbed to give them a long conductive area. That's why they're ribbed. But pipeline coatings aren't designed to withstand high voltages. And although some of them can withstand for a short period high voltages, most of them, the recommendation is to keep it below 2000 volts. Now, I don't want any coating people reaching for the phone to tell me that theirs will stand more. Yes, they will, some of them. But we have to take into account aging characteristics and different kinds of coatings. So we have a kind of rule of thumb measurement that we use, and we say we're going to stick with 2 kV as being a threshold after which we start to take notice. If you happen to have a 3-layer polyethylene coating, you can stand significantly higher voltages. What it does do to the coating, what it can do to the coating, is when this high voltage comes, it changes the characteristics of the coating and it makes it more absorbent. It will absorb more moisture, which over the long term will lead to an increase in cathodic protection current demand. Right, the risks to the pipelines under normal and operation conditions are essentially separated into inductive under normal operation, and under fault conditions there would be conductive. And as I mentioned, the DC is there all the time. And I've mentioned earlier that lightning strikes can affect the pipeline because the risk is increased by neighboring structures. You can see here a little image illustrating all of these things. We've included railways as well because they can be a source of interference, but we're mainly talking about solar farms and things like that. High voltage DC is something that is another form of interference for pipelines. It's so special and complicated that we're doing a separate presentation about HVDC tomorrow. But again, if you bear in mind the little seesaw and the moving charge, you'll be able to keep a firm grasp on what's actually happening. This is just to try and give you an impression about the radiation from the overhead power lines. And also we've included in this from AC trains, because AC trains generally run on 25,000 volts, and they can also cause problems to pipelines if you're parallel to them. And the coupling mechanisms there are inductive and conductive. There is a capacitive effect, which only happens on above ground pipelines. And that's what accounts for the people getting electric shocks when they're installing new pipelines and they're beneath overhead high voltage DC systems. And the challenge comes now because things are getting more complicated. We've got a lot more pylons around, got a lot more buried cables in the cities. People think because we're going into this cloud computing and storage age that that's good for power. You couldn't be more wrong. An awful lot of the projects we deal with are the high current demands for cloud storage systems. Obviously, they don't actually live in the clouds, they live in big buildings, but they get very hot and they need to be cooled, and there's all kinds of issues with that. So the problems are just going to get worse, and we are really lacking in good standardization and guidance at the moment. This is just to come back to the electrical shock. You can see the dependence upon the surface potential profile and the step distance and the touch separation distances. It's an art in itself, designing all these things to make sure people don't get electric shocks. And you might think to yourself, well, it doesn't affect me because I'm working with a buried pipeline. Well, unfortunately, when you build the pipeline, the cathodic protection guy has a cable brazed onto the pipe and brought up to the surface at a test post. And those test posts typically are connected to the pipe via this cable, via a stud, which is accessible from the outside of the test post. So the technician can just walk up, stick his probe on the stud and his widget in the ground and get a reading and see how things are. Well, if you're in an area which is at risk for electric shock, then these test posts have to be changed to make sure you can't touch them from the outside. And the other thing is, of course, is if you have a valve, an above ground valve that you need to adjust, you could easily have a voltage difference there, which could give you an electric shock. When we think that that might happen, we do put a special ground mat there, and all that does is level up the seesaw so it's equipotential, all at the same potential, so there's no slope. So the person standing there won't actually get an electric shock just from being there. Obviously, the biggest culprits for lightning are wind turbines, and there's no shortage of images on the internet or news bulletins saying that these things have burst into flames. Lightning strikes are, again, another rather specialized subject, and just as a byline, in the ISO working group that I'm the convener for, we are writing a technical report about lightning strikes and how they affect pipelines, because there's not really enough about pipelines in there and how we can deal with them. But you can expect around about 100,000 amps from a single strike, and it will affect the pipeline and it will travel to the nearest isolation joint. And if it exceeds the dielectric strength of the isolation joint, the joint will fail. But even if the protection device kicks in and it bypasses the insulation material, so it doesn't damage doesn't affect the dielectric properties of the insulating material, that voltage will be transferred into the AGI or the compressor station or the pump station. So it increases the risk to people who happen to be working there at the time. We've got quite a few examples of actual damage by lightning strikes and other effects caused by electrical interference, and you can see that they're quite marked. Over here there was an ignition. It was due to a lightning strike on a bush that was 5 meters away from the pipeline, and the voltage spread, and that was the result, that was the cause and the effect. I'm now going to quickly go through some of the typical sources of interference, and when I've been through those, I'm going to run through in a bit more detail with you a solar farm and what that does, I chose a solar farm because it's got both AC and DC components that are significant. People tend to think that a solar farm is just a collection of panels that gathers up the sunshine and puts it into a little box, and then it goes into the grid. But in actual fact, there's a lot more to them than that. This is what a battery energy storage system looks like. It looks pretty innocuous, but they are a source of DC interference to pipelines due to leakage, either due to battery or cable problems. And this is a high inertia synchronous condenser, to give it its full moniker. A bit later on, when we talk about solar panels and solar farms, I'll explain to you how we have to convert that DC into AC, because AC is what we have in our national grid. And you can't just add AC any old way you like. It has to be synchronized so it's perfectly in phase with the rest of the AC. Otherwise, you'll get problems. And that's what these devices are for. They're for synchronizing the AC that's feeding in to the DC. Now, before we go into the detail of the solar, this is just a quick table to show you what types of interference there will be from the different sources. So from battery energy systems, solar farms, and high voltage DC systems, there's got to be a change of DC to AC or AC to DC, whichever way around you're doing it. And that risk has to be assessed. Now, there's a fairly routine way that we tend to deal with assessing the risk. It depends a little bit on what phase you're assessing the risk. If it's at the planning approval stage, we have to do a preliminary assessment, which I'll come to a bit later. But a typical format would be to go to the existing pipeline and measure the AC and DC potentials over a 1 week period. That's to give a spread of loads and utilization. And that constitutes the baseline pipeline conditions, so that when the development proceeds and they power up the new system, we'll be able to compare the electrical interference on the pipeline with what's been delivered after the system's in operation. And the reason we do this is to protect both the pipeline operator and the developer, because if you work on the theoretical example, say of 15 volts being acceptable as an AC interference before you start to pay any attention to mitigation, let's say you were already suffering from 12 volts on your pipeline, which is below the threshold, but the pipeline operator is monitoring it and has got it all in hand. And the new system comes up. It's a humongous solar system with lots of converters and inverters, which I'll explain to you in a bit. And it only delivers 3 volts, which is a magnificent achievement. Unfortunately, it now puts you in the 15 volt region, where you'll be obliged, as the pipeline operator, to undertake further investigations and maybe mitigation. So it's important to get that done early on. We then do a preliminary assessment of the normal operation and the fault conditions of the system. And if we think of a solar farm, we look at the converters, which are devices from changing AC to DC. Depending on which way you wire it up, it either converts AC to DC or DC to AC. And it does it in a very crude way. It basically chops up the DC and then adds it back in a sinusoidal form, so that you get a nice waveform coming out, and it's now AC. Unfortunately, that chopping process does generate harmonics. And you might think, well, so what? It's no great issue. We're working at 50 hertz. Unfortunately, the harmonics can affect the levels of interference on the pipe, because depending upon the relationship of the harmonic to the original waveform, can add to the waveform and make it bigger than you expect. I did warn you that AC was a bit complicated. So we have to look at the harmonics that are generated. I'm pleased to say that the modern converters are much, much better because they're mainly processor controlled. They can be adjusted to reduce the harmonics to suitable levels. But if you look at some of the earlier converters, you'll see that quite a large amount of the real estate that they occupy is taken up with filters to filter off the harmonics. So let's move on a wee bit. See, we're running a bit short of time. Sorry, Sean. This is the overall approach that we adopt. It's an iterative process, especially at the preliminary phase, where we have to really look at how we do things. Now, I'm going to run through a PV system because it's got a little bit of everything. Basically, you start off with a solar panel that collects the DC. And you think to yourself, well, what is a solar panel? And you think, well, it's just some stuff that sits on a frame that collects juice, and it feeds that juice into a junction box. Well, the first point we have to worry about is the insulation between the solar panel and the frame it's sitting in, because we know from Ohm's law that if there's a low resistance between the solar panel and the frame is connected to the piling, and the piling is connected to the earth, there's a low resistance path there for the current to go. And of course, when you could have easily in excess of 100,000 solar panels on a big site, you can get quite a lot of leakage current, which can get onto your pipe. So the first point is this isolation resistance, which has to be measured and controlled. Next goes into a junction box. So you've got cables going through the ground. Sometimes they're on cable trays, sometimes they're buried. And of course, any contractor will always choose the cheapest cable he can find on the basis, the well-founded engineering basis that if it's cheaper, it must be better. So you've got the risk of leakage there, either in the junction box or in the cable itself. The junction box then feeds a charger, which charges the batteries. So you've got some electrical components in there and connection components. Then you've got the batteries, which have to remain isolated from Earth. And then the batteries are connected to an inverter, which converts the DC to AC. And then on the end of that, you might have a synchronization system to eventually feed it either to the consumer or to put it into the national grid. So leakage to Earth is always the problem. And that's what we've got to guard against, because that's where the damage will come to the pipe. Remember, we've only got less than a volt that we can tolerate in terms of change, of long-term change on the pipeline to take us out of the protected situation into the corrosion situation. And this is just a little schematic to show what sort of things have to be taken into consideration. But you have to magnify that to the size of a commercial field. And of course, Murphy's Law tells you that in the UK, where sunshine is a relatively rare event, we tend to have quite big arrays of these in order to connect enough current. So what are the key issues? Well, I guess I've tried to dilute it down here to show what the issues are, because people who operate alternative power systems get paid by how much juice they put into the grid. They don't mind running under less than ideal conditions. I don't know the figures, but let's say that they're happy to run on 50% efficiency, losing 50% of their current into the ground as a potential risk to the pipeline, provided they can still earn some money from squirting the other 50% in to the system. So they have a different threshold of acceptance than we do. And we like to make sure that they have SCADA systems incorporated to tell them when the risks are increasing, and a mechanism in process that will allow them to contact the authorized person in the pipeline operating department to deal with that risk. The stray current risks do depend very much on the configuration of the system, whether it's floating, whether it's earthed. And leakage currents can vary considerably. When it first goes into operation, it's all super. If they don't maintain the system over the years, the resistance between the panels and the earth will get lower, and so more will go on. So it's a difficult situation. We've got problems under fault conditions, which are electric shock and coating damage. The corrosion point of view, I explained a little earlier when we were talking about these sort of things. And we have to calculate the earth potential rise. You may find it referred to as EPR in the UK and much of Europe, GPR in the States as ground potential rise, and some people refer to it as ROEP, rise of earth potential. So we have to take into account those things as well. There are some standards that relate particularly to the criteria, and that's the 4 that are there. We are writing presently a new one, which is for HVDC. But those are the ones that basically deal with the electrical interference risk and the criteria that are acceptable. But all in all, there are approximately 36 international European standards and guidelines that are relevant for energy systems. There's one for the harmonics, for the converters. There's all sorts of things there. And you'll be pleased to know that your guild is very well represented on these groups that are preparing these standards and criteria. So just to summarize, really, it's all down to electrical interference, which is all down to difference of potentials, which we saw with the little seesaw example. And basically, the more current there is flying around, the worse it is. And the closer the pipeline is, the worse it is. So for pipeline operators, we need to quantify these risks and manage them in the same way that we manage all the other risks. So that's about it for today. That you've had the full 9 yards. I hope it hasn't been too unpalatable, and that you've been able to follow the logic and why we have to do the things we have to do. You can find a lot of information on the website that's shown here, both for almost every kind of AC and DC fault. And of course, you can always contact the authors, myself and Professor Charalambos. And of course, you can contact the Guild as well. So I do hope that's been of some use to you. If you've survived this webinar, you might like to chance your luck tomorrow in the high voltage DC one. But that's even more complicated, but it still hinges on the little charge on the plank of wood. So I'm going to stop sharing now and pass it back to Sean to handle any questions that anybody may have. You can either put them in the chat or just speak to us.
Brilliant, Ken. Thank you very much. I love how you can take the most complicated subject and turn it into a stickman on a seesaw. Brilliant. Martin's typing away there. Martin, do you just want to shout the comments out if you've got something, a question you want?
Yeah, sure. Thanks, Ken. Really, really interesting. Thanks, Sean. I mean, I was just wondering, are there rules of thumb for distances, or are there improved coatings you could do if you think you're going to be near one of these things, or does it all need a bespoke, in-depth assessment to come?
It's a very, very good questions there, Martin. The rule of thumb bit is hard because everything is so different, and within the various standards, they give recommendations for separation distances. The problem is they give different recommendations for the same thing. So we've, Professor Harlamos and I and some others have created a simplified calculation that people can do, which we're putting in the standards to work it out for yourself instead of depending on others. So the separation distance really always needs to be calculated if you want to be sure. And that's not a particularly hard calculation to do. The question of the coatings, you're right. If you felt you were at risk, you could put a super duper coating on some of the new viscoelastics and other kinds of self-healing systems are great. But so far, all of the ones that we've done, and we must have done 25 or 30 this year alone of these, it's always with an existing pipeline. And I'm always reluctant to interfere with a pipeline, even if it's got if it's an old pipeline with a rotten coating, because my experience has always been that as soon as you start to touch those kind of pipelines, your problems expand. You expose it and you think, oh, well, I'll repair this bit of coating. And then as you get to the end of the trench that they've opened for you, you see it still needs repairing, and you'll end up chasing it all the way back to the AGI and rewrapping it. So the real solution is in management of the interference, and there's marvelous data logging kit you can get now that measures corrosion rates and current densities and SCADA systems, automatic reporting. So it's more about, I suppose, the old Greek expression, which is well begun is half done. If you get the stall set out right and you do everything as well as you can within the construction, that's the best way to avoid the risks.
Yeah.
Nearly out of time. We've got another minute or two. Any other questions, or we are back tomorrow for another hour? Thomas,
Yeah, I was just going to ask, obviously, you mentioned that the quality of insulation between panels and the piles can degrade over time, and there's mechanisms to monitor that, and obviously the subsequent sort of increase in interference on the pipeline. How would a solar farm fix if you identified that they're starting to leak more current? What do they need to do to sort it?
Very, very good question, Thomas. Thanks. The well-designed systems have an automatic method to disconnect a group of panels. The panels are normally set up in strings or tables, and they can automatically isolate a string if they find that the resistance is low. The trick is what they set the threshold to as being low, which is why the pipeline operator needs to also maintain his own monitoring system to make sure that the interference isn't unacceptable. But the key to it all, really, Thomas, is a good rapport with the operators of the system so that they can tell you when you've got problems, and then you can take whatever preventative measures you want to take.
Okay, thank you.
no problem. We're at 1 o'clock. Ken's back on tomorrow, 12 till 1. Electrical impact assessment for pipelines due to high voltage DC. Hopefully we'll see you all back then. And thanks for your time today, Ken. Much appreciated.
No problem. Bye-bye. Bye-bye, everybody.